In order for a three-dimensional solid to be a polyhedron, it can have absolutely no rounded edges to it. All faces, the sides, must be flat. You can't have anything curved to it. So looking at these three pictures of solids, I can see that the first two, are going to be polyhedra. They have no curved edges to them. However, that third shape is not going to be. That cone is not going to be a polyhedron because it's got that rounded part to it. So we have our first two examples that are polyhedron. So they've asked us to go ahead and find the number of faces, the number of vertices, and the number of edges for each one. So faces are like sides, so it may be helpful if you had an example to actually hold in your hands and count. So this first example, if you need to see it, go find a box, go find a Kleenex box, for example, and hold in your hands, and that should help you actually count these pieces out. So faces or sides, flat surfaces, I can see that there's going to be 6 of those, the front and the back, the top and bottom, and the 2 sides. The vertices are all the points. So in the diagram, if I'm just using that, I can kind of see that it looks like there's 1, 2, 3, 4 in the front, and it looks like there's going to be 4 more in the back. And again, if you're holding one of these in your hands, you can actually count those corner pieces. There's going to be 8 vertices. And then edges are all the straight lines on there. So in the diagram, if you're using that, it helps to trace it out. So trace out 1, 2, 3, 4 lines in the front, 1, 2, 3, 4 more in the back. So I'm up to 8, and then 9, 10, 11, and 12 total connecting front to back. So 6, 8, and 12 must be my number of faces, vertices, and edges in that first figure. In the second polyhedron, if you want to pause the video right now and try on your own, go ahead and try counting those up on your own. Otherwise, we'll let it play through and work this out. This shape it's probably going to be harder to find. If you're in class, I have one of these if you want to hold it and count it. Otherwise, let's try our best to visualize it in our minds. So faces are going to be the flat surfaces. So I can see there's one flat surface along the bottom, that hexagon, and then there must be 6 triangles going up to wrap around to make the pyramid. So there must be a total of 7 faces. Again, if you have a hard time doing that, ask me in class to see this shape and I'll let you hold it and you can count them yourself. The vertices are going to be all the corner pieces. So again, on the diagram, let's kind of trace those or draw on those, I suppose. So there's 6 vertices along the bottom, the base of this, and then there's that one more at the peak of the pyramid. So there's a total of 7 vertices as well. Finally, for edges, probably helpful to draw over the diagram to help count those out. So there's going to be 6 along the bottom that make up the hexagon. So there's 6, 7, 8, and 9, 10, 11, and 12 to complete that. So 7 faces, 7 vertices, and 12 edges. Like polygons, polyhedron can both be convex or concave. Recall that concave meant the figure was dented, it had a cave in it. So our concave figure is going to be over here, it's been dented in. Our convex one means no dents in it, so this first picture is convex. Regular meant in a polygon, all angles and sides were congruent to each other. So a similar definition for polyhedron, I can see this first example has all those edges congruent because of those tick marks, so that could be a regular polygon, or polyhedron. And finally, let's work on naming polyhedron. Now, polyhedron are going to have 2 names. They're going to have a first name and they're going to have a last name. And their first name is always going to be named based on the shape of their base, no pun intended. So taking a look at this first diagram, to find my base, I can see that this is going to be a pyramid. Pyramids are usually easy for people to recognize because they think of Egypt and they imagine a pyramid coming up to a point. So in this case, pyramid is going to be one of my names, my last name actually. But the base in this, the part below the vertex, is this hexagon down here. So it's probably going to be helpful throughout this unit to shade and trace bases. So I get in the habit of doing that now. So that shape is my base. My base is a hexagon, a 6-sided figure. So the first name, I need to turn into an adjective though. I'm going to call it a hexagonal or a hexagonal pyramid for this name. So first name and last name. First name is based on the shape of its base. The last name is based on whether it's a pyramid or a prism. If I jump down to the shape below it, I can see I have another pyramid. This time, I'm going to call that the base. I can see that my base is going to be a triangle this time. So I'd call this a triangular, turn it into an adjective. And then the last name is going to be whether it's a pyramid or prism. Once again, I have a pyramid because from that base, I only have one base and the other end comes to a point. These next 2 figures are going to be examples of prisms. In this first picture, my base, I can consider at the bottom. Although in class we talked about how there's actually the top or the bottom or the front or the back in this picture, anything could really be the base. So my bases need to be sides that are parallel and congruent, so it's hard to tell with what I just scribbled, but the top and bottom are parallel and congruent, but so would the front and the back, or the two sides. So really in this box, as we used to call it, we could say that any pairs of sides would be the bases. But regardless, the shape of the base is going to be a rectangle, so I'm going to call that a rectangular. And then this is a prism because I do have two bases this time. So a rectangular prism. My last shape, people always want to call this a pyramid because they see triangles and they think pyramid. But this is not. This shape is a prism. It does have two bases. The bases are the sides that are parallel and congruent to each other. So in this case, that triangle along the bottom and that triangle along the top are the same exact triangles. And there's two bases. That's what made it a prism. And because the base is a triangle, I get the name triangular prism for the name of that polyhedron.